Hey y'all, I wanted to make a video to kind of go over some of the things in 5.5 again. I had some requests. I know that we had to go through this really fast in class, so I want to make sure that you get a little bit more of an explanation. So again, if we want an area function where we plug in an x value and what we get out is area from some fixed number a to our variable x, right? So our variable a is going to be some fixed number here where we're starting our area. X is going to be the end of the interval where we're finding the area. That's our variable. We're going to let that move. And so that is our variable up here. It becomes one of the bounds in our integral. So that's how we would find an area formula where when we plug x in, what we get out is the area underneath y equals some function f from x equals a to x equals whatever our variable is. And again, we use a dummy variable in here. Usually it's t. It could be any variable we want. We just don't usually use x so that we can keep our dummy variable separate from our actual variable, which is the end of our interval up here. Now, to find that area function, we just integrate this integral. We just do the definite integral, pretending that that x was just a number. We work with it just like if it were any other definite integral. So for instance, we did this one in class where we were told that we wanted to find the area underneath this function from a equals negative pi up to x, right? And so our a value is negative pi, so that's what went down here in our bottom bound. And then we want to let our variable be up here at x to be the end of our area. And since this was the function that I wanted to find the area under, that's the function that I put inside my integral because I'm finding the area underneath that one. And again, we just use t's instead of x's in here so that I can keep everything separate. And so to find our area function, you're going to integrate this just like normal using the fundamental theorem calculus part 1. You take the antiderivative of what's in here. You can use any antiderivative you want. So we pick c equals 0. So the antiderivative of 1 is t. The antiderivative of negative 6t is negative 3t squared. And the antiderivative of negative cosine of t is negative sine of t. And then and we picked c is 0 to make our life easier because any value would work. And then we evaluate that from our negative pi down here up to x. And so we plug our bounds in. We plug x in and we subtract what we get when we plug negative pi in. And after we plug all of that in and evaluate it, this is my area function. So when I plug an x value into this, what I get out is the area underneath this function from x equals negative pi to x equals whatever value I plug in. So let's just say I do the area function and I plug in, I don't know, pi over 2. Then when I plug pi over 2 in for my x value here, that's a pi over 2 plus pi plus 3 pi squared. And if I would add all of this together, you can put it in your calculator if you wanted to, what would come out is the area, the total area from x equals negative pi all the way up to pi over 2 underneath this 1 minus 6x minus cosine of x. So that's what this area function does. You plug an x value in, you get area out, and the way that you find it is setting up a definite integral with your variable in the bound. And then something that we mentioned is that the derivative of your area function. So this area function that we got out, the derivative of this is going to bring us back to our original function that we started with. And we did go through that in class. The derivative of this lovely function that we found is going to be 1 minus 6x minus the cosine of x plus a bunch of zeros, right? All of these numbers go away to 0. And so I just have this, which is the exact same function that I started with. I just have x's in there instead of t's. And that was the second piece of this fundamental theorem of calculus part 2, right? This first part tells you how to find your area function. The second part says that if you take the derivative of that antiderivative, a of x, you get back to your original function just with that variable swap, right? It was this variable plugged in there when we evaluate our bounds. That's where we end up because the derivative and the antiderivative cancel each other out and you end up right back where you started. You just get this fun little variable swap as part of that process. And so we kind of mentioned if instead of finding the area function itself, if I want the derivative of an area function, right? If the derivative is already in there and I want the derivative of this area function, this derivative and this integral, which is an antiderivative, right? We would use an antiderivative to evaluate it. Those are going to cancel each other out. And I'm going to end up right back at this original function, but I'm going to have x's instead of t's because I'm going to plug this value in as part of evaluating my bounds. And I'm going to end up right back where I started. I don't even have to go through all the work of finding the antiderivative and plugging in my bounds and then taking the derivative of that area function that I get out. I know I'm going to end up right back where I started, so I don't even have to do the work. I can just say what we're going to end up at. And then the second one, again, it wants me to find g prime of s, which is the derivative of g. And I'm told that g is this area function. It is the integral from 0 to s of sine squared of t dt. Because I'm finding the derivative of an integral, the derivative and the antiderivative are going to cancel each other out, and I'm going to end up back at my original function, but with that variable plugged in to get my variable swap. And I don't even have to do all the work. I know that what I'm going to get out of here is the sine squared of that s variable. And that's an s, not a 5. Sorry, it looks like a 5, but it's an s. It is that variable that we were given. Okay. So what if we have more than just a variable, right? With these, we had the variable by itself up here. What if I have more than just a variable? What if I have a whole function up here? I have stuff. Okay, so this one was kind of confusing. I want to do this one the long way, and then we'll kind of use that to come back up here to evaluate this one using the pattern. So let's do the long way on this. I want to find the derivative of this area function. So normally I would say, well, the derivative is going to cancel out the antiderivative, and I'm going to get back where I started, but with this plugged in. However, this is not just an x. This is stuff. And so it's going to change a little bit about how this works. So let's go the long way and see if we can figure out the pattern so that we can kind of get a shortcut for when we have a function up there instead of just an x. So the long way here is I'm going to find my area function g of x first. The way I'm going to do that is evaluating this definite integral, which is the integral from -2 to 5x to the third. And my function here is the sine of t dt. So if I evaluate this, I'm going to take the antiderivative of what I have in here, which is the sine of t. The antiderivative of sine is negative cosine of t. And I'm going to evaluate that from my bounds of -2 to 5x to the third. And now I can plug those in, and I get negative cosine of 5x to the third minus a negative cosine of -2. And so my area function g of x is negative cosine of 5x to the third plus whatever the cosine of -2 is. That's just a number. I can put it into my calculator, but it's just a number. And notice I'm not done. I was supposed to find g prime. So now if I take the derivative of this area function that we just found, the derivative of negative cosine of 5x to the third, this is a function inside a function. So we're going to do a chain rule here. Your outside function is negative cosine of x. Your inside function is 5x to the third. So you can do your chain rule here. The derivative, we're going forwards now. The derivative of negative cosine of some stuff. Let's see, the derivative of cosine is negative sine. So the derivative of negative cosine is positive sine. And the derivative of negative cosine of some stuff is positive sine of that same stuff, right? This is your f prime of g of x times the derivative of your stuff times g prime of x. The derivative of 5x to the third is 15x squared, right? This is from the chain rule. And the derivative of cosine of -2, this is just a number, so that is going to go away. You can write the 0, but we don't really need to because it's really nothing, right? It's 0, it doesn't count. So we can remove that, and this is our derivative. Now, let's try to come up with a formula here. So notice I still end up back at the function that I started with. I still end up back at the sign of my stuff, right? With this bound plugged in just like normal, right? Up here, we took this bound and we plugged it in, and that's where we ended up. But we didn't end up just with this. We ended up with the sign of my stuff plugged in times 15x squared, the derivative of my stuff. So if you have a function up here, right? If you have more than just a variable, if it's stuff, what you're going to end up with here is your original function inside of here with that stuff plugged in times the derivative of your stuff. The derivative of your stuff, this is what's going to pop out from this chain rule. So really, if we have a function up here in our top bound instead of just an x by itself, we can just plug our bound in, but then don't forget to multiply by the derivative of that function up there. So let's come back up here to this one. If I'm taking the derivative of this area function here, I'm going to end up with the derivative and the integral, the antiderivative, basically working against each other, and they're going to bring me back where I started, except I'm going to have this plugged in for p. And so when we do that, we are going to get 1 over that x squared plugged in for p, and p is squared, so I'm going to get x squared squared, right? So I'm going to have to plug my function into here. But because this is more than just an x, I'm going to multiply by the derivative of whatever's up there. The derivative of x squared is 2x. So what I should get out of this is 1 over x to the fourth times 2x. And this x will cancel one of these, and I'll have 3 left down here. So when I simplify this, what I get is a 2 on top and an x to the third on the bottom. This is what's going to come out of that. You could go the long way and you'll notice this is what you come out with as well. So if you have a function up there, it's going to be your original function with your stuff plugged in and then multiplied by the derivative of the stuff up there. Okay, and oh, that's not where I wanted to get that. For extra practice, this in-class worksheet that I handed out today, we kind of worked through a lot of that stuff at the beginning. Let's work through the stuff on the back, and we'll figure out how to make this all work and practice the section 5.5 stuff. Okay, so in this first bit, we're asked to use the fundamental theorem of calculus part 2 to find a formula for the function given here. Okay, this is just an area function. There's no derivative here. I'm not asked to find the derivative of an integral. I just have an integral and I have a variable up here. So this is an area function. I am asked to find the area function itself here. So to find the area function itself, we're just going to evaluate this definite integral just like we normally would, whether that was an x or whether it was a number. We're just going to do this integral. So to evaluate a definite integral, we are going to take our function in here and find its antiderivative. The antiderivative of e to the 3u is going to be e to the 3u, and we are going to divide by that 3 out front, because basically this is going to cancel with the 3 that's going to pop out from the chain rule when I take the derivative. So that's why that extra 1/3 is there. That's the antiderivative of e to the 3u. And then I'm going to say, now that I've found my antiderivative, I'm going to evaluate it from 4 to x. And so I'm now going to plug my top bound in, and I'm going to get 1/3 e to the 3x minus my bottom bound plugged in, which is 1/3 times e to the 3 times 4, which is e to the 12th. And nothing really here combines. If I wanted to, I could factor that 1/3 out, but nothing will really combine. So I'm just going to leave it as is. This is my area function. If I plugged an x value in, that would tell me the amount of area between e to the 3x and the x-axis from x equals 4 to x equals whatever number I plugged in for x. This is our area function. Cool. Now number 2. Again, I'm asked to find the formula for this integral. And notice I've got variables in both my top and bottom bounds here. We didn't really talk about this in class specifically, but honestly, with your bounds, if you have variables in your bound, that is an area function. So with this one, both your top and your bottom bounds are going to depend on the area that are on the value that you plug in. So this one's going to be a little weirder, because if I choose x equals 2, say, then I'm going to get the area. Let's see if I can spell. Yeah, that looks terrible. Let me try that again. We will get the area from x equals -2/2, which is -1, to x equals 2/4, which is 1/2. So I'm picking one x value, and that affects both the bottom and the top bounds, but I still get an area out of that. It's just harder to figure out exactly what my interval looks like, because both bounds are changing based on that x value. But that concept isn't going to change how we evaluate this. This is still an area function where when I plug an x value in, I get an area out. So to find that area function, I'm going to evaluate this definite integral just like normal. We're not going to overthink it. We're going to do the integral. The antiderivative of secant squared of t. What function has a derivative of secant squared? Yep, it's tangent. So this is going to be the tangent of t. That's my antiderivative. And I'm going to evaluate that from negative x over 2 to x over 4. And again, we're not going to overthink it. This notation says, hey, plug those bounds in. And I'm going to say, okay, I'm just going to plug them in. I'm going to plug the top bound in, and I'm going to get the tangent of x over 4. And I'm going to subtract what I get when I plug my bottom bound in, which when I do that, I get the tangent of negative x over 2. And if I plug x equals 2 into this function, I'm going to get a number out. And that number is going to represent the area between secant squared of x and the x-axis from x equals -1 to x equals 1/2. If I picked a different x value and plugged it in, I would get the area again between secant squared of x and the x-axis, but both my beginning and my ending x values would depend on that number that I'm plugging in. So that's what this looks like. And that's my area function. We can't really combine these because what's inside isn't the same. So I can't just add these together. The only simplification I can do, I have a negative inside a tangent function, and tangent is an odd function. I don't know if you remember your odd and your even identities from pre-calculus, but if you have an odd function, you can take the negative out and it ends up being multiplied by a negative. So this would be the negative tangent of positive x over 2. If I subtract a negative, that becomes a positive tangent of positive x over 2. And that's, again, changing this from a minus, a negative inside, to just a plus outside. That is trigonometric identities. If you don't remember those, it's fine. You can just leave it like this. If you remember those identities, this kind of looks better to most people's brains. Okay, so that's how you find area functions. You just evaluate the definite integral that you're given. You evaluate it, and you, my friend, have an area function. Where you plug x in, you get area out. Now, the other part of this is, what if I'm calculating the derivative of an integral? These are the things where you're asked to find a derivative of an integral. And again, to find an integral, we're going to use antiderivatives. So the derivative and the antiderivative are going to undo each other, and we're going to end up right back at this function that we started with, but with a variable swap. Now, this is just a variable by itself, so I can just go ahead and plug that in. And so the derivative and the integral are going to cancel out. I'm going to end up right back where I started at the secant function, except I'm going to have a t instead of an x, because that's going to be my variable in the end. And that is going to be what I get when I take the derivative of this integral. I don't even have to do it all out. Okay. And I guess before we move to the next one, it's often a question that I get when we cover these. What about that 100, right? Like we never do anything with this bottom bound when we're doing the derivative of the integral. We're just taking the top bound and plugging it in. Do we not care about that bottom number? Like, do we can just like ignore it? And the answer is yeah, kind of. And I keep wanting to do that. I'm going to go back to the example that we did in class. Where is this? Is it in here? Yes. Okay. So this one, I want to look at this one right here again. Notice our bottom bound here was negative pi. And in the end, we took a derivative of this integral, right? So really what we did was we took the derivative of this area function. When we take the derivative of this integral, they're going to cancel each other out. I'm going to end up right back where I started, but with a variable swap. And that's why we ended with 1 minus 6x minus the cosine of x. That's what we were going to end up with. And that's what we did end up with when we did this the long way. Now, this negative pi, where was this in this whole long worked out process? Well, the negative pi was here, and we plugged that in, and it gave us this part of my area function. Notice the variable up here gives us the piece of the area function with the variable in it. This negative pi down here basically gives me the part of my area function that's just a number. It gives me our plus c part of our function, basically. And when you do the derivative of this, what happens to the number part, that plus c part? When you do the derivative, it all just goes to 0 and it disappears anyway. So that's why when we take the derivative of the integral, it doesn't really matter what this bound is down here, because any part that would contribute is going to disappear with this derivative anyway. It's just going to go away. So yeah, we just kind of ignore that bottom bound because this is going to get rid of it anyway. And I keep doing that. It's in here. Someday I will learn. So yes, this bottom bound, when we are working with these, when you're doing the derivative of an area function, you can just ignore the bottom bound because the derivative is going to zero that out anyway. So the only one that really contributes is the variable part. And that's why we plug our top bound in, we get the variable swap, and we end up back where we started. Okay, and let's do this guy. We are asked to find the derivative with respect to s of this integral. And again, the derivative of an integral, those are going to zero each other out, right? They're going to undo each other. And we're going to end up right back where we started. And because I have a variable up here, this is an area function. And so I'm going to end up plugging that variable bound in. But my variable bound is not just the variable by itself, it's a function. It is stuff. So what I'm going to get out of this is this function here with my stuff plugged in. So I'm going to get the cosine of s plugged in for u to the fourth. And then because of the chain rule, I have to multiply by the derivative of what's up here. The derivative of the cosine of s is negative sine of s. Right, this pops out from the chain rule. And what I'm going to get left is the cosine to the fourth of s times negative sine of s. I don't want to leave the negative out here because your brain's going to turn it into subtraction. So I'm going to put this part out front. So I have the negative sine of s times the cosine to the fourth of s. And this is what's going to come out of this thing. So if you have more than just a variable by itself up here, you're going to plug that in and just don't forget to multiply by the derivative of your stuff. So just for fun, if I wanted to do another one, what if I want the derivative with respect to x of the area function of negative 3,219.7 up to e to the x? And I want the area that I'm going to find, the area underneath. My little f is going to be Let's just see. I'm going to make up something off the top of my head. I'm trying to think. How about the square root of 5 plus 9x to the negative 2. Oh, sorry, this has to be a t for some dummy variable. I don't want to get it confused with my x's. So we'll just do a t because that's what we've been doing. Okay. So I'm just going to make something up here. Okay. So we are asked, now that I've made this up, to find the derivative of this area function. I know it's an area function because I got a variable up here. And so I'm going to take the derivative of this integral. They're going to undo each other, and I'm going to end up back at this beautiful function. But with my variable swap, this is going to get plugged in. But it's more than just a variable by itself. So we can't forget to multiply by the derivative of it at the end. So I'm going to get the square root of 5 plus 9 times, instead of t, I'm going to plug e to the x in there, to the negative 2. Right? We're just plugging our top bound in, just like we did before. And then I have to multiply by the derivative of my upper bound here. The derivative of e to the x is e to the x. And this is what that thing is going to spit out. I guess we could simplify that a little bit. This is going to be the square root of 5 plus 9 e to the negative 2x. We can multiply those guys, and that e to the x is still going to stay on the outside. But that is what we would get out of this. And we can ignore this bottom bound because this derivative is going to make it go away anyway. So that's why we don't even consider that. Okay, I hope that helps with your 5.5 homework. And I'm sorry that everything was so fast. There's just never enough time. So hope that was helpful. Let me know if you have any questions, and happy calculusing over the weekend.